meeting, etc. And usually this thing takes a month, okay, of negotiations, where farmers put prices, and then the industry put price, and then they say, okay, there's no match. Let's start over. Now you know what these guys are willing to pay, and you know what the farmers want. Let's start over, and then they continue. And after a month, they get to a price which is acceptable. Imagine going to, for example, Sotheby and buying a painting. It takes a month before the seller and the buyer agree. That's not done, okay? But yeah, in the sugar beet industry in Denmark, this is done. So then they implemented that, and now it takes several hours of computers. Okay, for that application, it's fine. It's faster than what usually happens. But now imagine doing that for everything that you go on sale on the internet. No way, okay? No, nobody wants to do that and taking hours to do. So, but except for very few applications, it is really impractical. And we should really try to bring it more practical. And the reason is not that it looks quite interesting from an academic viewpoint. No, I think there's a fundamental reason why we need to continue doing research in that area. So what should be studied? So first of all, everything from above. You can look at what I mentioned, and then you can basically conclude. And I'm just going to give some examples. Invalidations or validations of our assumptions, I think, is very important. Now, how could we proceed? So the way that I think some people could proceed is, so first, it's known that if discrete logarithm would be easy, then computational Diffie-Hellman would be easy. And if this and computational Diffie-Hellman would be easy, then decisional Diffie-Hellman would be easy. And there is something else that Maurer introduced, which he called the decisional square Diffie-Hellman. And so there what you have, you're going to have an alpha and a beta, which beta is alpha to x. Then you're going to have a gamma. And the question is gamma equal to alpha to x to the power 2? It's kind of similar to the decisional Diffie-Hellman, but then having basically instead of an x here and a y, you have twice x. And so if this is easy, then this is obviously easy. And so what I think we should do is we basically are stuck. We don't even know how to prove that. But maybe what we should do is try to make something which looks easier. Okay? So find a hierarchy of problems that all seem easier than the decisional square Diffie-Hellman. Until you get so low that you have something that one can prove to be actually easy in a not too trivial way. Okay? You don't want to go so low that basically there's nothing to be proven anymore. And then the insight that you have by understanding that this problem that first of all, when you write it down, looks easy is not, then try to go back up and say, can we then prove something about the easiness of the problem above? So how far can you actually collapse this hierarchy? Okay, that's a possible approach. So another thing is verification tools for our proofs. How many people are working on that? I only know one paper that appeared at Crypto, where a bunch of French researchers from ENS, they actually looked at the very, very narrow context of group key distribution, and then they made an automatic tool to actually make proofs. Okay? But it's very little. By having basically estimated something between 50 and 75% of the proofs being correct, then we need some tools to actually check whether these proofs are good. Some researchers in formal methods claim that they could make progress on this. Some have actually looked at it. I spoke to a guy from France who actually looked at it and he gave up. So, but we cannot just continue this way and just having papers accepted primarily at conferences and even in some cases journals. And then basically find out that there was a bug in, and many of them nobody ever looked at, and basically maybe somebody will never look at it. It doesn't mean that they will not be used. That's the bad thing. So I also think that we need to do research on reducing the gap between theoretical and practical, in particularly when we have come so far, kind of now stopped. Can we not push this closer? So that's a question. Now, on the high level of what research topics we should look at, I think that there are enough problems in computer security that are not being looked at by cryptographers. So one can almost say that except for secure multi-party computation, cryptography today, by researchers in cryptography, is still being viewed as communication security. And why the heck would that be? I don't see a reason for that. I mean, when you look, we came from privacy and then authenticity, etc. Why would we stop at communication security? And so an issue is that we evidently may have to adapt some of the problems so that they become easy to study. And so, for example, one question is, can we make proven secure operating systems? Now, everybody, in particular people who are working on computer security, are going to say, this is way too hard. Now, wait a moment. If you look at Rabin's paper, and if you look at Goldwasser and Mikale, they had security defined in a very, very narrow way. Okay? And they had then some scheme which was completely impractical. So I'm not saying a practical operating system. I'm not saying secure against everything. I'm saying something very narrow and very slow. Okay? And then, in so many years' time, let's extend basically what the security definition means, and then make it more practical. So far I know, nobody's working on that in the crypto community. Proven database security. There are some people, cryptographers, who have looked at certain aspects of the database security, but there are other problems that actually should be looked at, and I'm just going to give one example from inference. There are more examples. If you start to think about it, there are many more examples. And this example is actually coming from Denning's book, The Cold War. It's a Cold War example. So what she writes in her book is that the Rand Incorporation modified during the Cold War maps so that the Soviets could not use them to find the exact location of strategic positions in the United States. And what it does after the transformation is that with a not too bad accuracy, you can actually measure the distance between two places. But using these maps to accurately know where something is located is not. Now, evidently now with satellites, etc., and GPS, all these things is useless. But it's a nice example. And so when you think about this in the context of AIS, so you remember this boat story, then you can think about broadcast encryption with asymmetric trust in the receiver. That means that if you basically are a ship nearby another ship, you should know where that other ship is to avoid a collision. Okay? So there you are trusted. But if you are farther away, as for example, you have a container on that ship, and you know it's going to take a week anyway, or maybe more, before your ship is going to arrive, why the heck do you have to know the exact position of that ship? There is no need for that. Okay? So you have an asymmetric trust in the receiver, and so that means that depending on your need, the need to know, you will actually get the data, but quite inaccurate. So you may know that except if there's a major storm or something, that your ship is expected to arrive that day. And the closer it gets to the port, the more precisely you will know when your container is going to arrive. So that's basically inspired by Denning's book, and it's quite nice. It's basically coming from the computer security, but then actually looking at it from a crypto. So nobody that I know actually has looked into this aspect. So I was told to finish at aim for 5:20. It's now 5:22, so it's time to conclude. So although cryptography is not perfect and may not have prevented catastrophes so far, there are plenty of examples that demonstrate its importance. The academic research has flourished to a degree never anticipated by pioneers as Diffie. So I heard not too long ago a talk by Diffie in which he said somebody would ask him in 1976, are you going ever to imagine that there will be a call from NIST for making block ciphers, and that's not a call to basically NSA, but a call to the academic community, and then have a bunch of Europeans design it and become a standard in the United States. And not just a standard, but actually being approved for the use of the encryption of top secret data in the United States. So I think that this is a major success for the research. And other examples include modes of operations that also were designed by academia. So there have definitely been successes. So some proven secure crypto systems are truly practical, and other ones get close. So I also think that's quite a success. So overall, I think that the research in crypto is actually in good shape. However, some redirection should be considered within the community. And for those of you who are young researchers, I think it's quite exciting, in particular when you like discrete math and complexity theory, to actually apply it in crypto. But I think you should look at the following advice. I think you should spend 20% or 30% of your time trying to break assumptions. Okay? Because if nobody's going to do it, in particular the young people aren't going to do it, then what happens, the situation will get worse and worse and worse. Now I didn't say 50% or 60%, okay? So, but now if you make progress, then your advisor might say, oh, wait a moment. Yeah, you should really, really continue on that. That's actually much better than everything else that you were doing. Why don't you make your thesis from what you've been doing? But that's only after you make your progress. So it's kind of, you're spending some time in case. Now the probability something will come out is kind of estimated to be low, but you never know that you're lucky. The payoff would actually be great. I also think that you shouldn't trust theoreticians when they say something is practical. Okay? And so, I'm particularly looking at research that turned idealist. I'm not going to mention names, but some people have been looking at practical issues from the ivory tower instead of originating from an actually real need. And I think we need to look at balancing. What do we really need? And are we going to continue on making more and more and more papers on topics that so far look never going to be implemented? And so besides considering the classical problems, consider some not so well studied topics that might actually be more relevant. And so finally, I would like to say that proven security is exciting. It is really exciting, but it's very easy to make mistakes. And I will tell you that basically the paper that appeared in the 2008, if my memory is correct, with my co-author, was going to appear in the IEEE transactional information theory, had a bug. And that bug was found after the acceptance of the journal paper. But the galleys were not out yet, and so we actually stopped. We asked the editor to stop this paper. Lucky enough, my co-author could sort out the bug. But I think we have to be honest. I think we as cryptographers have to be honest. Making proofs is hard, okay? And it's actually a student of me who designed a protocol for some generalization of what that was going to appear in IEEE transactions on information theory. And I broke his scheme. And he said, oh, you know, if you can break my scheme, I can break your scheme. And so then he showed me, and so basically he was right. We were lucky that we could fix it. So it is indeed very, very hard. And many, many people have made the mistakes. And I think we should be basically honest and saying, be very, 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 very careful. Check every statement. And when you have longer and longer proofs, which in particularly are encouraged in the complexity community, if you have a paper with basically the proof is too easy, too convincing that it is correct, then it's kind of, yeah, this is too easy, let's reject this. But what people have to realize is that the longer and longer the proofs are, the more and more complex the protocols, the more and more complex checking that these things are correct. And so, should we accept papers that have long proofs? I'm not so sure of that. I think that sometimes people need to think about trying to make the proof shorter. Now, I know that the proof of Fermat's last theorem was quite long, etc. But what happened there is that they basically very, very, very carefully checked it. And they, as you know, a bug was also found in that proof. And then the authors had to restart. So we shouldn't be, we have to be careful. That's basically my conclusion. Any questions?